Welcome to another deep dive today. I know our listeners are like real philosophy enthusiasts, and they love getting into these complex ideas. So we're going to untangle something pretty fascinating today. It's called the Epsilon calculus.
Yeah, it's kind of a hidden gem, in the world of logic, but it's got some surprising connections to philosophical questions you might be wrestling with yourself.
Absolutely. Our guide for today is the Stanford Encyclopedia of Philosophy's entry on the Epsilon calculus. And I think what makes this deep dive so intriguing is that it's not just some abstract, formalism. It was developed by David Hilbert, and he had a huge vision, to actually solve some foundational problems in mathematics.
Yeah.
And as we'll see, it kind of touches on the very nature of how we pick things out in the world and how we refer to them.
It does. It really does. That act of referring, that kind of points to something and says, this is it. That has some really profound implications for metaphysics and philosophy of language, don't you think?
Absolutely.
Yeah.
So to set the stage, can you give us a little reminder of the historical context that surrounded the Epsilon calculus?
Okay, so picture the world of mathematics, in like the early 20th century.
Okay.
There's this crisis, brewing paradoxes have emerged in set theory and logic,
Oh,
and it's shaking the foundations of the field.
yeah.
Think about Russell's paradox.
Right.
The set of all sets that don't contain themselves,
Yeah.
it leads to a contradiction.
Yeah, if it contains itself, it shouldn't. And if it doesn't, it should.
Exactly. It's
Yeah.
a real head scratcher.
Yeah.
These paradoxes really threw the consistency of mathematics into question.
Right.
So mathematicians were looking for a way to kind of ground the field on solid logical principles.
And that's where David Hilbert and his program come in, right?
Exactly. Hilbert was a giant in mathematics,
Okay.
and he had this ambitious program to prove the consistency of mathematics.
Okay.
He wanted to show that, mathematical reasoning was free from contradictions. We weren't going to just stumble upon, some hidden paradox that would bring the whole thing crashing down.
Right, a noble goal, for
Yeah.
sure.
Yeah, definitely.
So how did he propose to do that?
Well, Hilbert's idea was to formalize all of mathematics within a very rigorous, logical system, and then use what he called finitary methods to prove that system's consistency.
Okay.
And these finitary methods were supposed to be absolutely concrete, beyond any doubt.
Yeah.
And this would provide this bedrock of certainty for mathematical reasoning.
So it's like a rule book. You create an ultimate rule book for mathematics, and then you prove that by following those rules, you're not going to hit any dead ends.
That's a great analogy.
Okay.
And this is where the Epsilon calculus kind of enters the picture.
Right.
It was a key tool that Hilbert developed as part of this program.
Okay. I'm starting to get a sense of the historical backdrop, but let's kind of dive into the heart of the matter.
Sure.
How does the Epsilon calculus work?
Okay.
What's the big idea?
So the key innovation of the Epsilon calculus is this new logical operator, the Epsilon operator,
Okay.
often written as the Greek letter epsilon, followed by a variable,
Okay.
kind of like this epsilon x.
And what does that do?
It's like a powerful search function for mathematical objects.
Okay.
It lets us pick out a specific object that satisfies a given condition,
Okay.
even if we don't know exactly which object that is.
Can you give me a concrete example?
Okay, sure.
Yeah.
So let's say we have a statement like, there exists a number x such that x plus 2 equals 5.
Right.
We know this statement is true, right?
Yeah, of course it's 3.
Right, exactly. But pretend for a minute we don't know
Okay.
that the epsilon operator lets us say, okay, I don't know which number satisfies this condition,
Yeah.
but I know there is one, so let's just call it epsilon x plus 2 equals 5.
So epsilon x plus 2 equals 5 is like a placeholder for this unknown number.
Exactly. It's a way to refer to that specific number that makes the statement true, even if we haven't actually figured out what it is yet. It's like saying, hey, there's this thing out there that fits the bill,
Right.
and I'm going to call it this for now.
Yeah. That's a clever way to deal with existence without having to actually identify the object.
Exactly. And it gets even more interesting
Okay.
when we introduce Hilbert's transfinite axiom.
Okay.
This axiom states that if a statement is true for some x, it's also true for the x picked out by the epsilon operator applied to that statement.
So in our example, because we know that some number satisfies x plus 2 equals 5,
Right.
we can just automatically conclude that the number denoted by epsilon x plus 2 equals 5 also satisfies the equation.
Exactly. It might seem a little strange at first, but this axiom is crucial because it gives the epsilon calculus its power.
Okay.
It allows us to manipulate these arbitrary objects picked out by the epsilon operator
Right.
in a consistent and logically sound way.
I see the potential here. It's like you're saying, I don't need to know all the details about this object,
Right.
but I can still reason about it
Yeah.
based on the conditions that define it.
Exactly, and that actually has some philosophical
Oh,
implications.
really?
We're essentially saying that the act of of picking out an object
Yeah.
can be based solely on a description,
Okay.
on a set of conditions that the object satisfies.
That connects to so many debates in philosophy of language
It does.
about like definite descriptions
Yes.
and how we refer to things in the world. I'm already seeing how this is challenging some of my own assumptions about these things.
That's the beauty of these formal systems, you know? They
Yeah.
really make us re-examine, our intuitions about language and logic.
Yeah, so we've got this epsilon operator that acts like a search function. We've got this transfinite axiom that lets us reason about these objects.
Right.
But can these epsilon terms always pick out the same object? Or is there some ambiguity there?
That's a great question.
Yeah.
And it really gets to the heart of what makes epsilon terms so unique.
Okay.
And it turns out that epsilon terms can be non-deterministic.
Okay.
They might not always pick out the same object in different situations.
Can you give me an example?
Yeah, so consider the epsilon term epsilon x equals a, or x equals b.
Okay.
So this term is basically saying, give me an object that's either a or b.
Okay.
Now, depending on the context, this epsilon term could refer to A or it could refer to B.
Yeah.
And the calculus itself doesn't actually tell us which one to pick.
So there's a sort of inherent ambiguity baked into the epsilon calculus.
There is, and that ambiguity is both a source of its power
Okay.
and a potential challenge.
Right.
It allows for this flexibility
Right.
in how we use epsilon terms.
Yeah.
But it also means that we need to be very careful about how we interpret them.
I can see how that would raise some eyebrows among philosophers
Yeah.
who like to have things very precisely defined.
Absolutely. And, it's led to some really interesting debates
Right.
about the philosophical foundations
Oh,
of
okay.
the epsilon calculus.
Yeah.
But before we kind of get into those debates, let's explore how this seemingly simple addition, this epsilon operator,
Yeah.
can actually change the whole landscape of logic itself.
Okay. I'm ready.
All right. Welcome back to our deep dive, into this fascinating world of the epsilon calculus. We've seen how it introduces this powerful new tool, right? This epsilon operator.
Right.
It's like a search function for mathematical objects.
Yeah, and I'm especially intrigued by how this seemingly simple addition,
Yeah.
this epsilon operator,
Right.
how it can shake things up in the world of logic.
Yeah.
You mentioned that it changes the landscape of logic itself.
It does.
That's a pretty bold claim.
It is, but it's a claim that Hilbert and his followers were able to substantiate.
Okay.
The epsilon calculus is more expressive than ordinary predicate logic.
Okay.
It can capture, these more nuanced relationships and concepts,
Okay.
and it can do it in this quantifier-free way.
Okay, now you've got my attention.
Right.
What does it mean for the epsilon calculus to be more expressive?
So think about how we typically use quantifiers,
Oh.
like for all, and there exists in predicate logic.
Right.
These quantifiers are fundamental building blocks of our logical language.
Right, like all men are mortal or there exists a prime number greater than 100.
Exactly.
Yeah.
But here's the amazing thing.
Okay.
We can actually define these quantifiers in terms of the epsilon operator.
Really?
We can translate statements involving for all and there exists
Okay.
into equivalent statements that use only the epsilon operator and logical connectives, like and or and not.
So the epsilon calculus can do everything that predicate logic can do,
Yeah,
but it can do it without relying on those explicit quantifiers.
that's right. It can do it in a quantifier-free way.
That's kind of mind-blowing.
It is.
Yeah.
And this embedding of predicate logic within the epsilon calculus
Yeah,
has
yeah.
some really profound implications.
Right.
It suggests that the epsilon operator,
Yeah.
this seemingly simple search function,
Right.
is actually a fundamental logical concept,
Okay.
maybe even more fundamental than the quantifiers that we're so used to.
It's like the epsilon operator is a more primitive building block,
Uh-huh.
and we can kind of construct these more complex structures of predicate logic on top of it.
That's a great analogy. And this reduction to a quantifier-free system
Yeah.
was particularly appealing to Hilbert,
Okay.
because it aligned with his finitary philosophy.
Right.
He saw the epsilon calculus as a way to represent, these complex mathematical ideas
Yeah.
in a more concrete, manageable way.
So the epsilon calculus wasn't just a tool for proving the consistency of mathematics.
Right.
It was also a way to kind of reshape our understanding of logic itself.
Absolutely. It was this bold attempt to reconceptualize
Yeah.
the foundations of mathematics and logic, and it really had, a ripple effect throughout these fields.
I'm eager to delve into those implications,
Yeah.
but first let's talk about these epsilon theorems. You mentioned them earlier.
Yeah.
It's kind of key results that shed light on the relationship
Right.
between the epsilon calculus and traditional predicate logic.
Yeah.
Could you elaborate on those a bit?
Sure. So the epsilon theorems are kind of like bridges, between these two worlds of logic.
Okay.
They demonstrate that despite this added expressive power of the epsilon calculus,
Right.
it doesn't fundamentally change the set of theorems that we can prove.
So we can think of the epsilon calculus as a kind of scaffolding,
Yeah.
a temporary structure that helps us build proofs,
Uh-huh.
but it can be removed without affecting the final result.
That's a great way to put it. Yeah.
Okay?
The first epsilon theorem in particular tells us that, if we have a proof of a formula
Yeah.
that uses epsilon terms, we can always find an equivalent proof
Okay.
that doesn't use epsilon terms at all.
So the epsilon terms, these arbitrary objects,
Right.
they can play a role in the reasoning process,
Yeah,
but they're not essential to the proof of the final theorems.
exactly. And that's quite reassuring in a way, right?
It is, yeah.
It means that, the epsilon calculus,
Yeah.
despite its unique features,
Right.
doesn't lead to some completely different kind of mathematics or logic.
Right.
It's more like an extension,
Okay.
a richer language
Yeah.
that allows us to kind of express and prove things in new and insightful ways.
I can see how this would have been encouraging for Hilbert
Yeah.
and his program.
Yeah.
It suggests that the epsilon calculus, despite its use of these seemingly strange arbitrary objects,
Right.
could still be a reliable tool for proving the consistency of more traditional mathematical theories.
Exactly. Hilbert and Bernays, in fact, used the first epsilon theorem to prove the consistency of elementary geometry,
Wow.
showcasing, the potential of the epsilon calculus for these foundational purposes.
Right.
They showed that, epsilon terms acting as these ideal geometric objects
Go ahead.
could be eliminated from proofs about real geometric statements
All right.
without actually affecting the truth of those statements.
That's a concrete example of how the epsilon calculus can bridge the gap
Yeah.
between this abstract logical formalism and actual mathematical practice.
Exactly. And the epsilon theorems offer a deeper philosophical insight as well. They suggest that there is a kind of harmony between different ways of representing mathematical knowledge.
Okay.
We can use these more abstract, perhaps even non-constructive methods
Right.
involving arbitrary objects.
Yep.
But ultimately, those methods can be grounded in more concrete traditional proofs.
This is starting to sound like a reconciliation between different schools of thought
Yeah,
in the foundations of mathematics.
right.
Like the epsilon calculus is offering a way to bridge the gap between those who emphasize concrete constructions
Uh-huh.
and those who are more comfortable working with these more abstract, non-constructive methods.
That's a profound observation.
Okay.
The epsilon calculus, in a sense, allows us to have our cake and eat it too.
Right.
We can work with this, flexibility and expressive power of these arbitrary objects.
Yeah.
But we can also rest assured
Yeah.
that those objects can ultimately be eliminated,
Right.
revealing this underlying constructive core of our reasoning.
This deep dive is really illuminating the philosophical richness of the epsilon calculus.
Good.
But before we get too carried away with the philosophical implications,
Sure.
I'm curious to learn more about the practical applications of this system.
Yeah.
You mentioned earlier that the epsilon calculus has connections to other areas of logic,
Right.
like Herbrand's theorem.
Yes.
Can you tell me a little bit more about that connection?
Absolutely. So Herbrand's theorem is this fundamental result in logic
Okay.
that deals with the relationship between existential statements and their proofs.
Okay.
It basically tells us that if we can prove a statement of the form there exists, an x such that a of x is true,
Okay.
then we can actually find a finite number of specific terms. Let's call them tip 1 and t2 and so on,
Yeah.
such that at least one of the statements, a of t1, a of t2, and so on, is guaranteed to be true.
So it's like if we know something exists, we can always find some concrete examples of that
Exactly.
that seems intuitively plausible. But I imagine proving it rigorously requires some pretty sophisticated machinery.
It does. And here's where the epsilon calculus comes in.
Okay.
Hilbert and Bernays, using the tools of the epsilon calculus, provided the first complete and correct proof
Wow.
of Herbrand's theorem.
Okay.
They showed how the epsilon operator could be used to systematically construct these concrete terms
Right.
that witness the truth of this existential statement.
So the epsilon calculus, which started as a tool for proving consistency,
Right.
turns out to have this unexpected connection
Yeah.
to this fundamental theorem about the structure of logical proofs.
That's right. It highlights the deep insights that the epsilon calculus can provide into the nature of logical reasoning.
That's fascinating.
It's not just about manipulating symbols.
Right.
It's about understanding this relationship between existence,
Yeah.
proof,
Yeah.
and the structure of mathematical arguments.
This connection to Herbrand's theorem also sheds new light on the power of the epsilon operator.
Yeah.
It's not just a way to refer to arbitrary objects.
Yeah.
It's also a key to unlocking these hidden structures within proofs,
Uh-huh.
providing a deeper understanding of how logical arguments actually work.
Exactly. And that deeper understanding has ramifications for, the very foundations of mathematics.
Yeah.
It allows us to see connections
Yeah.
between seemingly disparate areas of logic
Yeah.
and to develop new methods for analyzing, the strength and consistency of mathematical theories.
It feels like we're starting to see the epsilon calculus as more than just a technical tool.
Yeah.
It's becoming a lens through which we can view the very nature of logic proof and mathematical truth.
That's a beautiful way to put it,
Yeah.
The epsilon calculus, despite its initial focus on Hilbert's program,
Right.
has really opened up these new avenues of exploration in logic and the foundations of mathematics.
Right.
It's challenged our assumptions about this relationship between language and mathematics. And it's provided us with, new tools for understanding the structure of logical reasoning.
This deep dive is really living up to its name.
Good.
But before we continue our exploration, let's pause here for a moment and kind of let these ideas sink in.
Sounds good.
Okay, so we've been on quite the journey with the epsilon calculus from Hilbert's program to prove the consistency of mathematics,
Right.
these surprising connections to Herbrand's theorem,
Yeah.
and even a hint of how it can kind of reshape our understanding of logic itself.
It's amazing how this, seemingly niche area of logic can touch on such fundamental questions.
Yeah, and as promised, we're going to delve even deeper into those philosophical implications of the epsilon calculus in this final part of our deep dive.
Right.
I'm especially fascinated by this concept of arbitrary objects, which you mentioned a few times.
Right.
They seem to be at the heart of what makes the epsilon calculus so unique
Yeah.
and potentially so controversial.
They are definitely a key feature, and they've led to some, pretty spirited debates among philosophers. So, an arbitrary object in the context of the epsilon calculus is an object that's picked out solely by its satisfying a certain condition.
Right.
We don't need to know which object it is or even whether it has any other properties beyond those specified by the condition.
So it's like saying, give me a philosopher who has written about the epsilon calculus.
Perfect example.
I'm not specifying which philosopher, just that one exists with that property.
Exactly. Now, think about how this relates to, how we use language.
Okay.
We often use descriptions to refer to objects, even if we don't know, all their details.
Right.
We might talk about, the inventor of the wheel or the first person to climb Mount Everest, even though we might not know their names or have complete knowledge of their lives.
Right. It's like we're saying there's this thing out there that fits this description, and I'm going to refer to it even though I don't have all the specifics.
Exactly. And the epsilon calculus gives us a way to kind of formalize this kind of reference, We can use epsilon terms to represent these objects that are picked out solely by their satisfying a certain condition.
So it's like the epsilon calculus is giving us a more precise way to talk about these partially specified objects.
Yes.
These things that we can refer to, even if we don't have complete knowledge of them.
Exactly. And this has some interesting consequences for our understanding of meaning and reference.
Okay.
Some philosophers have argued that the epsilon calculus actually challenges these traditional theories of reference, which often assume that we need to have some kind of direct acquaintance with an object
Yeah.
in order to refer to it.
Right, like in the classic Phrygian view,
Exactly.
where a name refers to an object by virtue of some mental connection between the speaker and the object.
Right, but the epsilon calculus suggests that we can refer to objects based solely on descriptions,
Yeah.
without any need for this direct acquaintance or mental grasp.
Yeah.
It's as if the description itself is sufficient to pick out the object,
Okay.
to bring it into our discourse, even if it remains, somewhat mysterious and partially specified.
This is starting to sound like a challenge to the idea that meaning is grounded in some kind of mental representation.
It is as if the epsilon calculus is saying, meaning can emerge from the way we use language to pick out objects in the world,
Yeah.
even if those objects remain somewhat elusive.
That's really fascinating.
It is, and it's one of the reasons why the Epsilon calculus has been so thought-provoking for philosophers of language.
Right.
It forces us to re-examine our assumptions about how language hooks onto the world,
Yeah.
how meaning is generated, and what it means to refer to something.
It's also interesting to think about the implications for metaphysics,
Yeah,
for our understanding of the nature of reality itself.
right.
You mentioned earlier that some philosophers see the epsilon calculus as supporting a view where objects are, in a sense, brought into existence
Right.
by our descriptions of them.
It's a radical idea,
Yeah.
but it's one that some philosophers have taken very seriously. The thought is that, objects don't have this independent mind, independent existence prior to our descriptions of them.
Okay.
Rather, it's our act of describing, of specifying conditions
Right.
that kind of brings them into our conceptual world,
Yeah.
that makes them available for us to talk and think about.
So it's not that the epsilon calculus denies the existence of an external world,
Right.
but it's more like that it suggests that our access to that world,
Yeah.
our ability to carve it up into objects and categories, is fundamentally shaped by our linguistic and conceptual practices.
Exactly. The Epsilon calculus doesn't, solve the age-old debates between realism and idealism.
Right.
But it does provide a fascinating new perspective on these debates.
Yeah.
It highlights this active role that language plays
Right.
in shaping our understanding of reality.
It's almost as if the epsilon operator, with its ability to pick out objects based on descriptions,
Right.
it's kind of a microcosm of this larger philosophical point.
Yeah.
It shows us how we can bring things into focus, how we can create a space for them in our discourse, simply by specifying the conditions that they satisfy.
That's a beautiful way to put it. The Epsilon calculus, with its seemingly abstract formalism,
Yeah.
turns out to have these, profound connections to the way we experience and understand the world.
This deep dive has been a real mind bender. We've journeyed from the technical intricacies of Hilbert's program to these deep philosophical questions about meaning reference
Right.
and the nature of reality itself.
It's been a pleasure exploring these ideas with you.
Likewise.
The Epsilon calculus, despite its challenges and controversies, stands as a testament to the power of human thought to really push the boundaries of logic, mathematics, and philosophy.
I couldn't agree more. And it's a reminder that even the most abstract and seemingly esoteric areas of inquiry can have these profound implications for how we understand ourselves and the world around us.
And as a final thought, for our listeners to ponder, if the Epsilon calculus can challenge our assumptions about how we refer to objects and even the nature of existence, what other hidden gems might be waiting to be discovered in this vast landscape of logic and mathematics?
That's a great question to leave us with. It seems like there's always more to explore, more connections to make, and more insights to uncover.
Yeah.
So thank you for joining us on this deep dive into the epsilon calculus.
Yes, thank you.
We hope it has sparked your curiosity and inspired you to keep asking those big philosophical questions.